Okay, welcome again. We are discussing some elementary signals, and we have discussed exponential, both real and complex valued, and we have also discussed the sinusoidal signals. In this video, we'll be taking a very special function or a signal that we use a lot in signals and systems, and that signal is called, so I think this will be the fourth one, and this is let me just increase size. What's known as a step function. Yeah, step signal, doesn't matter. Fine. Now mathematically it's a very simple signal, so let me just define this signal, that the continuous time version of step function, yeah, signal, it actually has its own notation. It is denoted by u of t and is given as, it is defined as that u of t will have a value of 1 for time greater than equivalent to 0. It will have a value of 0 for time less than 0. Fine. So if I am to plot it, let me just quickly do a small plot here. If I am to plot this, let me just try to save some space. Okay, like this. So this will be my time axis. This will be u of t. So it has a value of 1. Say this is 1 for time greater than 0. So this will be my unit step. We say a step function, अब इसका value 1 है, so we say it is a unit step function in the sense that its amplitude has a value of t. Simple सा signal है, nothing that complex. And then we will have it as discrete time version, which will be a similar kind of a signal. So discrete time, so the discrete time version of step function, yeah, unit step function, it is defined as, so we have the normal change. Instead of u of t, I will be writing u square brackets n. Then it will have values for 1 for sample instances greater than 0, and then 0 for n less than 0. Graphically speaking, it will be a similar kind of a signal. Just the difference, we won't have a continuous time scale, we'll have a discrete time scale. So if this is value of 1, it will be sample value here, then sample value here, likewise. Fine. So this is 0, 1, 2, 3, and 4. Okay. So it's a very important signal because it is simple, and I told you that we follow a particular kind of methodology in engineering in general, and in system analysis in particular, that we always start with the simple cases. Since this is a simple signal, we often try to express or characterize the system by applying this kind of signal at the input and see what is the behavior of my system to a unit step function. Then we go for complicated. So we will do that analysis. Fine. And another property is that you can always shift it. If you remember, we discussed the basic operations that can be performed on the signal. We discussed 3 when those independent variable operations are concerned. We had scaling, we had reflection, we had shifting. Now you can apply all those basic operations on these elementary signals. Fine. And it has a property that it can be used to construct another discontinuous waveforms, this unit step signal. Fine. Just as an example, because we may be using this in our numerical analysis. So if I have a signal, say x of n, discrete time case that is, it has a value 1 for this range, and outside this range it is 0. Right? It's a general kind of a signal. So first of all let me just plot it. You should always plot a signal, it gives you a better understanding. So this is my general signal, let me just plot it, although I don't need a negative axis, but still. Okay, so it is defined for points from 0 to 9, so I will quickly list those points. This is 0, 1, 2, 3, 4, 5, 6, should I use a different color anyways, 8, 9 and 10. And at these points from 0 to 9 it has a unit value. So if this is 1, so it has a value like this. Then outside this it has 0 values. Fine. Now I can always express this general signal x of n in terms of my unit step. Fine. So let me first define my general unit step signal, that is u of n. It is defined as a signal which has a value of 1 for n greater than equivalent to 0 and 0 for n less than 0. So graphically it will be something, yeah, it's just, since I've already drawn it. Okay, so just to differentiate, this is basically my x of n and this is u of n, in the sense that it will have samples defined at all these points. So dot dot dot. Fine, this is my u of n. Now if I define a shifted unit step, if I define a signal, say u of n minus 10, this is a basic shifting operation. आपकी याददाश्त के लिए, if I just say कि we had the shifting operation defined at this, like this, n minus n naught, and if n naught was positive, then you are shifting your signal towards right. Fine, but that amount. Now here n naught is 10 and it is positive, so I'll be shifting my basic unit step function towards right by 10. Okay, so if I try to write it mathematically, so mathematically it will be like this, and 0 otherwise. And if I try to plot it, I'll have to use a new plot here. If I try to plot it, like this, let me use a different color. So this will be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and so on. Fine. Now it is shifted by 10 units. So somewhere here, so let me just number them. And then it will start from here. and it will continue at all these discrete sample points jitne bhi hai, 11 12 13 14 15 16 and so on. So this is my u of n minus 10. Right? Now if I subtract this waveform from this general unit step, in other words, mathematically I can say u of n minus u of n minus 10. So what will happen? All the samples after 10, that is this, they will be cancelled because they will be subtracted by the sample point. So what will be left will be a signal that has samples from 0 to 9, which is basically your x of n. So I can say this is my x of n. So your general signal x of n, it has been expressed as an arithmetic difference of the normal unit step and the shifted unit step. Right? Since जैसे मैंने कहा कि this is a very important function in the sense that when we try to characterize a particular system, we often see what is the response of this system to a unit step signal. Fine. Then we in fact say that this is the unit step response. Right? So if I am using this kind of a generalization wherein every arbitrary signal can be expressed as an algebraic sum of unit step, it kind of makes my analysis easy because it's already known what is the unit step response of my system. So if I am able to express my input signal in terms of my unit step signals, आपका जो एनालिसिस है या कैरेक्टराइजेशन ऑफ अ सिस्टम है या सिस्टम रेस्पॉन्स डिटरमाइन करना है, it becomes a bit easier. Fine. So we will be using this property a lot. So I'll stop here. In the next video, we will take another very important signal from an analysis and characterization point of view. That is the impulse function or the impulse signal. That we'll take in the next video.